Innar Liiv, and I'm from Tallinn, Estonia. I'm really honored to be chairing the keynote lecture, the first keynote lecture of this conference by David Hand, who's a British statistician, emeritus professor at Imperial College, or thinker of data analytics, and he was elected a fellow of British Academy in 2003. He has served twice as president of Royal Statistics Society. He has been appointed Officer of Order of the British Empire in 2013, just to mention a really few of the awards. And in short, he has done data science decades and decades before it was actually called data science. This talk will be about dark data, which, as I understand, is about the data which you don't have, perhaps data which you wish you had, you hope you had, you thought you had, but nevertheless, you don't have. So we are really honored to have you here. The floor is yours.
Thank you very much indeed. I'd like to begin by thanking Zeynep for inviting me to speak at this conference. This conference is really very much at the cutting edge. Data for policy is what it's all about. This is what is going to revolutionize the human condition. But I'm especially pleased to talk at this conference because it gives me an opportunity to speak about my recent book, Dark Data, Why What You Don't Know Matters, to advertise my book, if you like. That book was published in February at the start of the pandemic, so that to some extent, with a sort of painful irony, dark data disappeared into something of a black hole. This gives me, I hope, a chance to sort of try to rectify that. So let me kick off by reminding you of all these sorts of phrases which you see in the media, in blogs, in newspapers, television, all the time: big data, alternative data, observational data, artificial intelligence, data exhaust. These phrases crop up all over the place all the time. All of those phrases, though, are concerned with the data you do have and its potential for improving the human condition. What they don't tell you is about the data you don't have. They don't tell you about the problems that can arise because you're missing some crucial data. They don't say that the data you don't have, the dark data, can be even more important than the data you do have. So let me kick off with some of my favorite examples, just to sort of give you a flavor of what I'm talking about. You might have seen me talk about these examples before, because I think they really convey the ideas very nicely. So my first example is a little anecdote, one which many of you will be familiar with: elephant powder. You're walking down the road and you come across an elderly man putting little piles of powder in the center of the road, and you ask him what he's doing. He says, "It's elephant powder, it's to keep the elephants away." And you say, of course, "But there are no elephants here." And he says, "Yes, it's wonderfully effective, isn't it?" Of course, what he's missing is what would happen if he didn't put the elephant powder down. He might discover that that was just as effective at keeping the elephants away, and then he might go on to discover that there were no elephants to be kept away. He's missing some of important information. He's missing some dark data. Here's another story which has exactly the same abstract mathematical structure as the elephant powder example, but much more serious consequences. Before I go on, Innar, can I just ask, on my screen, I've got images down the right-hand side of the screen which are hiding part of the picture. Can you see the whole picture?
Yes, we can.
Okay, thank you very much indeed, thanks. Okay, so back to my measles eradication example. Around the year 1985, about 1.2 million people per year were dying from measles. By the present time, though, that a modern medical miracle, vaccination, of course, has shrunk that to about 100,000 deaths per year worldwide because of measles. In fact, since the turn of the century, over the course of the 21st century, about 25 million lives have been saved because of vaccination. In fact, it's far worse than that. It's recently been discovered that measles damages the immune system, and it's thought that about 4 times as many people die of other things that they wouldn't have died of if measles hadn't damaged their immune system. So we're really talking about 125 million lives, not just 25 million, since the turn of the century saved by vaccination. But now, put yourself in the position of a parent trying to decide whether their child should be vaccinated. They might say, well, none of my neighbors or friends or workmates, none of my child's school friends have died of measles. I think the danger is exaggerated. Of course, what they're missing, just like the elephant powder man, is what would happen if people don't vaccinate. It's exactly the same mathematical structure, but much more serious consequences. And here's a third example, Hurricane Sandy. October 2012, the second most costly hurricane to hit the American seaboard, eastern seaboard. $75 billion worth of damage, 200 people killed. But the point about Hurricane Sandy is that it was accompanied by, that physical storm was accompanied by a Twitter storm. 20 million tweets were sent. And Twitter tells you what's happening, when it's happening, where it's happening, to whom it's happening. You know exactly where to send the emergency services. Except imagine a community which had been completely obliterated by Hurricane Sandy. All the phone masts were down, all the power was down. You wouldn't get any tweets from them, so you wouldn't know that's really where you needed to send the emergency services, dark data. And my final little example, a policy example, is concerned with the UK poll tax example, fiasco a few years ago, where the data was basically collected from a small quote, this is from a report, a small group of exceptionally bright officials and junior people who talked incessantly to each other, but it left out data. They deliberately excluded local government treasurers and possible reaction from taxpayers. So again, they were missing crucial data with essentially disastrous consequences. My final introductory example is a little bit more elaborate. It concerns the relative rate of heart disease in Japan and the US. Here are the numbers. The heart disease, the number of men who die from heart attack per year per 100,000 people in Japan is about 41, and in the US it's more than twice that, it's 87. So what are the risk factors for this heart disease? One risk factor is smoking. If you smoke, it's bad for you, and the proportion of men who smoke in Japan is more than twice as high as in America. So that's a bit puzzling. One might have expected it to be the opposite, given the way the heart disease death rates go. Another risk factor is systolic blood pressure. Again, it's worse in Japan than in the US on average. A third risk factor is cholesterol level. Again, worse in Japan than in the US, not much worse, but nevertheless worse. Now, obviously, all these factors are correlated, but nevertheless, we've got three risk factors, all pointing in the direction which should suggest that Japan should have a higher death rate from heart disease than the US. So what's going on? Now, of course, you all know what's going on. It's known to be because of the protective, the Japanese have a diet which is high in fish, which has an oil in it, which contains a substance called omega-3, which is protective against heart attacks. But consider this. Heart attacks, in fact, are a low-status disease in Japan. They imply manual labor, digging roads and so on, whereas strokes are high-status disease in Japan, implying cerebral labor, the sort of things that all you guys do. So isn't it just possible that what would be diagnosed as a heart attack in Japan might be preferentially diagnosed as in the US, might be preferentially described as classified as a stroke in Japan? I'm not saying it necessarily is, but what we're potentially missing here is dark data because of the not necessarily misclassifications, but different types of classifications. Of course, if this explanation was right, then we would expect to see a higher stroke rate in Japan than in the US. And in fact, we do. It's 50% higher. Now, let me be clear about what I'm saying here. I'm not saying that omega-3 is not protective against heart disease. I'm saying it's quite likely that there are other factors like this one here, which is a dark data factor, things we haven't thought of. I imagine in this case that both of these factors are relevant. Okay, so what is dark data? Well, perhaps you really want today's data, but all you have is yesterday's. After all, we never have data about the future, only about the past. Perhaps your sample's distorted, perhaps some cases are missing. This is common, as we'll see. Perhaps the data are inaccurate or rounded. Measurement is always imperfect. No measurement is taken to an infinite number of decimal places. Perhaps the data do exist, you have got them, but you haven't bothered to look at them. I'll put it here, they might be gently decaying in a data warehouse, unlooked at because they were collected for compliance reasons. Perhaps the tax office required you to collect the data and you have to keep it for 6 years, but you never look at it or analyze it, a different kind of dark data, what I'm going to mention again in a moment. But perhaps what you really want to know is what data you would have collected if you'd done something else entirely different. But of course, you can't do everything, so you have to make choices. Okay, so this is the cover of my book, Dark Data, Why What You Don't Know Matters. And in that book, I produce a taxonomy of 15 types of dark data. 2 of these types, I'm not going to go through all 15, I'm just going to give you a flavor. 2 of the types will be very familiar to you. The data we know are missing and data we don't know are missing. They'll be familiar to you because Donald Rumsfeld called them known unknowns and unknown unknowns. This is an example of the first, the known unknowns. This is from a survey. I've got age, height, weight, and sex variables, columns showing those. Each row represents one person. And you can see that in the age column, 3 of the values are NA, not available. They're missing. They weren't recorded. If we look at the first row, if we look at the second row, we see an NA for age there. Now, we know that this person had an age. We just don't know what the age was. So it's the known unknown. Here's an example of unknown unknowns. People who don't respond to a question in a blog. We don't know who read the blog. We don't know how many people who was interested in the question that we asked, who might have replied but didn't have time to reply. Or something. We don't know anything about those people. They are very clearly unknown unknowns. My third type is choosing just some cases. So for example, if you measured or sought to measure the national economic performance of a country based on surveys from companies, ignoring those which no longer existed because they failed, you would get a misleading impression. Gartner, the company Gartner, organization Gartner, has a definition of dark data, which is in fact my type 3 dark data. They refer to the information assets organizations collect, but don't analyze, like my tax compliance example earlier on. My 4th type of dark data are self-selection. So, for instance, customers who shop at a particular store. I might be interested in making drawing some general conclusion about consumers in a country. But if I just select the data from particular shops or a particular shop, I could be misled because maybe these customers aren't like others. Another example are people who opt in to a database of health records. They're quite likely to be very different from those who opt out. They're clearly different in that they opt in or opt out, one or the other. So they might differ in other ways. So again, the dark data, those who've opted out, might lead me to draw misleading conclusions. So here are the other 11 types of dark data. I'm not going to go through them all, but since my book appeared just before the COVID crisis, and since the COVID pandemic is riddled with dark data issues, I thought I'd take the opportunity just to mention a few in the context of these other 11 types. The first type is missing variables. My examples so far have been about missing cases, particular individuals or particular values in records. This type is when you're missing a whole variable. So for example, at the beginning of the COVID pandemic, it wasn't clear, it took a while before it became apparent that age, deprivation, and other factors had an impact on whether one was likely to contract the illness and how severely one was likely to get it. Those would be entirely missing variables if they hadn't been measured. And one has to ask oneself, what else have we missed? My second type here, the 6th type, is data which might have been. So these are counterfactuals. I've already mentioned them, but they're counterfactuals. And I think something like 120 clinical trials of vaccines for COVID are being conducted around the world at the moment. They're trying to tell you, okay, we know what happens if we give this person treatment A. What would have happened? What data might have been had we given them treatment B? Definitions of data are a nice little example, this one. On the 28th of May, the UK was reporting 267,000 cases of COVID and 37,000 deaths. In contrast, on that date, Russia was reporting 50% more cases, but only 1/9 as many deaths. Now, why might this be? It might be that the Russians are sort of immune to the illness, or more probably some other dark data explanation. Perhaps, for example, they had different definitions of COVID, of death from COVID. Did you die with COVID or from COVID? Did the death require a formal COVID test, or was it just based on symptoms, and so on? So different definitions hiding what's going on, dark data. Another example, another COVID example, summaries of data. Averages, of course, you all know, conceal things about ranges, extremes, skewness, and so on. And in the context of COVID, governments are fond of putting out figures such as 20 infections per day per 100,000 people, which is perfectly fine as a summary. But if you actually look at a map of COVID infections, you'll find that there are hotspots. You'll find areas where there are many more than 20 per 100,000, and most of the country where there are far fewer than 20 per 100,000. So the summaries are hiding what's going on. Again, it's dark data. And finally, from this slide, feedback and gaming. This is an interesting source of dark data. And we have Donald Trump, of course, came up with a wonderful example of this when he observed that you can reduce the apparent COVID infection rate by reducing the number of tests. Okay, now I have as I said, 15 different types of dark data, but I have a warning. The different types can occur together. Just because you've identified a selection bias problem in your data or a rounding problem in your data doesn't mean that the other types haven't also occurred. You really have to be on the alert for all possible types occurring. And I'll just give you one little example of this. IBM's sort of flagship AI program is called Watson. It's proven very good at things like Go and chess. And 2016, I think it did very well at the television quiz show Jeopardy, a sort of general knowledge quiz. And it was thought to be, you know, this was something of a breakthrough. It was breaking away from well-defined worlds like chess to the real world. So they launched a program applying Watson to cancer diagnosis and treatment, Watson for oncology. A report about this, however, said Watson had phenomenal natural language processing skills, but in these records, data might be missing, one type of dark data. It might be written down in an ambiguous way, another type, or out of chronological order, multiple types coming together. As a consequence, this report said, IBM internal documents show that its Watson supercomputer often spits out erroneous cancer treatment advice, and so on. I should say that IBM contests this conclusion in this report, but I really wanted to draw your attention to the data might be missing, written down in an ambiguous way, or out of chronological order. Multiple ways that dark data can arise in any one context. So this is all very well. In fact, I could stop there because the real aim of this talk is to get you worried about dark data, make you very anxious so that you rush out and buy the book to discover what you should do about it. But I'll have mercy and I'll push on by saying, so what do we do about it? Well, one thing we can do is get extra data. You can increase the sample size to reduce the variance. You can get what are called gold samples. If you're carrying out a screening thing, you can get some of the people that you might have rejected and actually investigate those. Not many of them, small number, but it will allow you to build better models. You can repeat your contacts in a survey to tackle declining response rates, like the labour force survey here. Sometimes you need to try something different altogether. This is a genuine quote from the Actuary magazine in 2006, where it says, a couple of months ago, I invited all 16,000 of you to participate in our online survey concerning the sex of actuarial offspring. And then they went on to say, well, I'm pleased to say that a number of you, 13 in fact, not 13,000, just 13, replied. Clearly they need to find, I mean, all of the data are dark here, basically. They need to find some completely different strategy if they really want to answer this question. Another approach is to use expected properties of the data. So for example, this is a plot of ambulance response times on the horizontal axis against number of calls, a number of ambulances responding in that time on the vertical. And there is a peak at just before 8 minutes. And in fact, the target response time was 8 minutes. So clearly there's some kind of manipulation of the data going on here, hiding what's really going on. You know, 8 minutes, 30 seconds, I'll call it 8 minutes, that kind of thing. Funnel plots are used in, especially in clinical trials, of course. On the horizontal axis, we've got an effect size, how effective the drug is, whether it has a positive effect or a negative effect. And on the vertical axis, we've got sample size. And you can see that for small samples, which are at the bottom of the screen, we've got a large horizontal variance. The effect size isn't estimated very accurately. But at the top, the horizontal variance, is estimated very accurately. We've got a very low sample variance. We've got large sample sizes up there, but there's a gap at the bottom left of this graph. There aren't very many points there. This suggests that results which just by chance have produced low values, negative values in this example, don't actually get written up and appear in the literature. So there's bias distortion going on. And you can spot that from this graph. And then Benford's law. This is from a big anti-money laundering project I was involved in many years ago. Benford's law tells you that for certain kinds of data sets, the distribution you would expect for the most significant digit, so the 1 in 1,000 or 1 million or 10 million. And initially you might think that the number of 1s and 2s and 3s for the most significant digit will be equal. But in fact, for certain kinds of data sets, 1s occur more often, and there are theoretical reasons why this, about 30%, well, 27% of the time, whereas 9s occur about 5% of the time. The bar chart, the black bar chart, shows you the expected distribution. The orange bar chart shows you the distribution we got from analysing very big financial transactions in this money laundering investigation, very different from the expected distribution. There are also more general strategies. So complete case analysis. So here's this survey that I put up before. In complete case analysis, we just include those rows which had all of the values recorded. And you can see immediately that you might have problems because there's a lot of missing data here. We would eliminate a lot of the rows. In fact, if you look closely, you'll see in this example, we would eliminate all of the rows. We wouldn't have any data at all if we try to follow this strategy. Another strategy is to use all the available data. So let's look at age. There are 7 recorded values of age there. We could just use those values and analyze those. The trouble with that is that the 7 people who have recorded age are different from the 8 people who have recorded height. So if we try to do an analysis based on this, we'd be using different samples. If it was height and weight, and all the shorter people preferentially had not recorded their value, and all the heavier people had preferentially not recorded their value, we might think that the population consisted of lots of incredibly tall, skinny people. We'd be misled. Another more general strategy is to find substitutes for missing values, imputation. So one very common strategy, you get this in statistical software, is to use the average of observed values. So let's come back to age, for example. There are 7 values of age there, recorded, calculate their average and plug that in for the NAs in age. The trouble with that, of course, is that, well, there are many problems with it, but one of the problems is that it's going to artificially reduce the variance. It's unlikely that those 3 missing NAs, those 3 missing values, really would have the same value. That's one problem. A particular variant of this imputation strategy, which is, no, I was going to say is used, but which has been used in clinical trials, is last observation carried forward. This is where, when you're measuring the state of a patient over time and you miss a value, you use the value which you took just before they dropped out or whatever. This is generally not a good idea. And it's pretty obvious, really, if in a clinical trial or any other situation, for example, you're measuring repeatedly over time. The reason for that is probably because you're interested in understanding how things change over time. So going back to the previous value rather defeats the object. And in fact, this approach has come under a lot of criticism. It's been called the most inappropriate technique and lots of far ruder things. More generally, a potential for imputation, a potential method is to use observed variables to predict the unobserved variables. I should have said at the start when I started talking about imputation, the reason that this is an attractive approach is that if you impute a value, a substitute for the missing values, then you can use standard statistical tools. You don't have to develop a special tool which can cope with data which is chock full of holes. Anyway, use observed values to predict unobserved values. This leads to a high-level strategy for tackling dark data, basically shining a light on it. What you do is use what you do know about what you don't know. And I'm going to describe three sorts of situations. This is based on what I'm about to describe is based on Donald Rubin's taxonomy of missing data. I've changed the terminology. You'll see why in a moment, because I think his terminology is a bit inaccessible. But three different reasons for this particular kind of dark data, for missing data. The first is what I've called NDD. It stands for not data dependent. It's missing for reasons unrelated to the data. So for example, with Ofqual in the A-level fiasco in mind, I'm thinking of sickness might prevent students from sitting the exam. And sickness is going to attack the able and unable, less able students at random. So it's not data dependent, it's just random across the data set. Seen data dependent, SDD, is where it's missing for reasons related to the data you do have. So for example, a school based on previous tests by the student, data you have got, might discourage less able students from sitting the exam. And then unseen data dependent, UDD, is missing because of the values you would have got. So perhaps a student realized the night before that they've revised the wrong material, so they didn't turn up to sit the exam. Quite clearly, the value they would have got is going to be low, a poor score, because they revised the wrong material, so they didn't sit the exam. So let's work through this example in a little bit of detail. My objective is to estimate what would be the average final exam score for a school if every student had been examined. But the data are previous test results for all students, but a final exam score only for those who sat it. And students dropped out for the reasons that I've just described, and which I'm going to recapitulate in a second. So this is the data. This is the situation. I want the average final exam score, and these are the data I've got. Okay, so this is the complete data. I plotted on the vertical axis the exam result, if I knew it, and on the horizontal axis the previous test results. If I had all the data, this is what it would look like. This is NDD, not data dependent. This is when sickness prevented the students from sitting the exam. Now, at random in the whole distribution, I just lost students. So there's no bias introduced here. I can estimate the final exam result using the observed values for the exam result. I will have a higher variance, so less accurate estimate, but there's no bias introduced. So not data dependent, NDD, straightforward. Here's the complete data again. And here's the SDD, seen data dependent. This is when the school discouraged less able students from sitting the exam. And if you look at my data, you see that there are fewer students with a final exam result if they scored less than 0 on previous test results. The left half of the graph has fewer data points than in the complete data. I can't use the observed exam scores now to calculate the exam results for the average exam result for the school, because it would be biased upwards because of all the missing ones on the left end, which tend to be lower. So I have to do something about this. What I'm going to do is fit a regression model, linear regression, and I can do that perfectly well because at each value of the previous test result, I've got an unbiased distribution of exam results for that value of the previous test result. So my regression model would be unaffected by this kind of distortion. And once I've fitted the regression model, I can interpolate for the students, for those on the left, the values, the missing values which they would have had, and then calculate the overall exam result, the overall average exam result. And then finally, there's my complete data again, and here's my unseen data dependent. And you can see that now, this is when the student decided not to sit the exam because they thought they knew they would do poorly. So I've got lighter, fewer students sitting the exam in the bottom half of the graph. Now I can't fit my regression line because at any value of previous test results, any vertical line through this graph, I will get, I've got a distorted sample. It will produce a biased estimate. In fact, the regression line, will, if you fitted a linear regression line, it would be biased downward. And really, I would fit a non-linear regression line. So I can't use my simple modeling and interpolation approach here. Of course, if I knew the result, if I knew the data were missing for exactly the reason I described here, I could do something about it, but that's leading me into more than I want to get into now. Okay, so up until this point, I've described some of the dangers of dark data. I've described some of the ways you can begin to tackle it. I'm now going to flip things on its head and talk about how you can take advantage of it. I call it the strategic application of ignorance. Well, one thing you can do is reveal by concealing. And this is one of my favorite examples, a real example. A long time ago now, in 1927, Holland adopted a confidential system of reporting causes of death. And as a consequence of that confidential system being adopted, the number attributed to syphilis increased dramatically. This is a really nice example because previously invisible, the cause of death, data is being made visible. And you're doing that by making other data invisible. Now, of course, you use these ideas all the time. You might want to keep your medical and financial records secret. You do that using passwords, which keep data dark. And of course, they need to be kept dark themselves, which, as you know, opens up all sorts of ethical challenges, especially in the context that we've heard about earlier today. Let me say a little bit, I'm drawing to an end. Let me say a little bit about the dark data perspective on familiar methods, because it's possible to flip things on their heads, flip standard methods on their heads. This is very obvious in certain contexts, like in sample surveys, where we generally describe these as you sample a small proportion, like 10% of a population. But flipping things on its head, that is, of course, equivalent to making 90% of the population dark. You can look at it from the other way round. And in clinical trials, randomized controlled trials, I talk about clinical trials, but these could, of course, be in social context, policy context as well. What you do is necessarily hide which treatment is given, a blinding, very sort of literal interpretation of dark data. More advanced statistical tools can also be regarded as dark data. What you're doing here is using what I call the principle of generating data that could have been. It's not data you got, but it's data that you could have got. It's dark data. So, for example, you can generate multiple data sets using the proposed model. You have an idea, a theory, a conjecture, a model. You generate lots of data from that and see how it conforms to the real data. That, of course, is simulation, nothing more or less. You can generate extra randomly, slightly perturbed, jittered data to produce extra copies, and then analyze all of the data, including this data that could have arisen, this dark data. That leads you to smoothing. It's another way of looking at smoothing in data, regularization. You can take multiple subsamples of the data. That's, of course, bootstrap methods to estimate variances and so on. You can generate copies of misclassified data points in classification problems, diagnostic problems, or classification problems. That's called boosting. Or, even more generally, you can use additional, imprecisely specified data. And that, of course, is exactly what Bayesian statistics does. All of these ideas use data that you didn't see, but you could have seen, as I've illustrated there, leading to much of modern statistics, very powerful statistical tools. Okay, I've got, I think, 3 more slides which look at another aspect of all this. You guys all use sophisticated software to look at the data in different ways. You fit this model and that, you summarize it in this way, you identify suspicious points and so on. You display the data. And the point is that you do that with sometimes you've got massive data sets and you couldn't look at them by hand. You do that using software tools which provide windows on the data. But windows lie between you and the outside. If you like, that's almost a definition of a window. And windows only give you particular views. They don't rotate around the garden or whatever. So you need to ask yourself, are you sure the tool's doing what you want it to do, the software tool? How do you know it hasn't got mistakes built in? Are its default choices what you want? The Royal Statistical Society recently had a comment on this. It said, any statistical algorithm embeds a range of judgments and choices. It's not simply a technically obvious and neutral procedure. So just as you should be wary of dark data, what I've been talking about up to this point, so you should be wary of the algorithms. And I think there are 4 points you should consider, 4 primary points. Obviously, one can expand this ad infinitum. First, how will the system respond to changes? We all know that the world's fundamentally non-stationary. Financial crisis 2008, pandemic 2020, what next? If we've got algorithms, AI systems, inbuilt data analyses, tools which make assumptions, how are they going to respond? Second, how effective is the interaction between humans and these tools and the algorithms? I'm thinking especially of machine learning tools and so on, AI tools, because they function in a human environment. COVID tests provide another example. Medical diagnostic tests have false positives and false negative rates, but those are not absolute properties of the tests. They also depend on how well the test is administered, how well that swab from the back of the throat is taken. So the algorithms and methods all work in a human environment. But there's more. These things also work in an algorithm environment. They work with other algorithms. We find algorithms summarizing data, which are fed to other algorithms to analyze the data, and so on. So they also work in an algorithmic context. The Internet of Things is, of course, going to be generating all sorts of data, but then you've got sort of algorithms stacked on algorithms. And then finally, how will the software be updated? Human revision or autonomous? The Tay chatbot disaster, which you'll all be familiar with, I'm sure, is a nice example of how things can go wrong when they update themselves autonomously. There's something called the Validate AI initiative, which was launched about a year ago, had a conference about a year ago, which is looking at these sorts of problems, these algorithmic sorts of problems in detail. So let me wind up. First, I spoke about, drew your attention to, although you didn't need it, drawing to this, the immense potential of data and data science for improving the human condition. You're all leaders in this area, you all know about that. I spoke about the risks arising from dark data and from, just in the last few slides, algorithmic opacity. The bottom line, the take-home point from all of this is that you still have to think. You cannot just rely on these things to get it right. They can only do what they are built to do. So I'd like to conclude there. Thank you for listening and fading into dark data, leaving me with the book. Thank you very much indeed.
Wonderful. Thank you, David. And let's now move on to questions and answers. And please use the chat window to write all your questions. And I would perhaps start by one of my own. So if we go back 60 years to the writings of Sokal and Sneath in numerical taxonomy, then they wrote that if you want to start analyzing data, then actually before measurement and collection, you have to discover what to measure. And my question, if we think about this conference, people want to analyze data to support evidence-informed policymaking. What would you recommend? What to measure, or how to start solving that issue?
Yeah, I always believe that one should start with the question: what do you want to know? What are you trying to find out? Now, I've seen examples of big corporations with massive sort of legacy data sets bringing in consultants and saying to them, data mining consultants saying, not me, I should say, saying to them, find something interesting in these data, and then fail 3 months on it and then fail to do so. And this is because they weren't directed. What do you regard as interesting? What would be a worthwhile discovery? What sort of things do you want to find out? What kind of questions are you trying to answer? So I think that has to be the starting point. Once you know the sort of area, it doesn't have to be too specific necessarily. Once you know the sort of area that you're trying to look for, the sort of thing you're trying to look for, then you can say, okay, well, how would we look for that? How would we recognize it when we saw it? What sort of things should we be measuring in order to spot this kind of thing? So that's my view.
Okay, and I will try to group now the different, if some questions are repeating some themes. Some of them were answered already in the lecture, but I will still repeat some of them. So first theme is research. What do you think, whether the pressure to publish might leave behind dark data? So if all the fields don't have like journals of negative results, what should they do?
I'm really glad you asked that question. Yes, the book has a whole chapter on scientific reproducibility, these sorts of questions. I didn't put it in here, partly because I only had half an hour, and partly because I wanted to shift more towards the sort of policy, government, that administrative kind of issues. But yeah, problems of lack of reproducibility in science, problems of dark data in science, again, these sorts of issues can crop up in many ways, and they are an explanation for a lot of the concern that's recently been raised. So I think that is very important. The best thing I can do is direct people to the book, but there are various sort of prime examples. Regression to the mean is a common phenomenon which occurs in scientific publication. When big effects are discovered in science, the size of an effect might be big because it has two underlying factors. One is it's fundamentally quite large, and two, measurement error, which is always there, has tended to be large for the particular observations they got. So overall, they've got a particularly large value, so they write that up and publish it. And then when people come to replicate that, the real underlying aspect is still large, but the measurement error could just as well be small as large. So the big effect shrinks, it seems to disappear. So this is one reason why for the sort of reproducibility crisis. And there are other things like p-hacking, where people trawl through large data sets looking in lots of different places. The physicists call it the look elsewhere effect, looking in lots of different places for something which is, if you like, significant, and then just publishing that, ignoring all the other things. So there are many reasons for this sort of problem in science. Okay, and next question. So actually there's the sequence of questions from Stefan from New York. So to what extent does dark data relate to poor questioning? If we improve the question we seek to answer, would that enable us to answer the data we need, and which ones may be dark? And do we have dark questions? Yeah, that's also a very nice question. You're absolutely right. To some extent, it does. Over 25 years ago now, I wrote a paper about how, giving many examples of how statistical questions were often not very clearly formulated. They were ambiguously formulated so that you could get misleading, indeed wrong answers, because they didn't really ask the precise question that was wanted. So I think the short answer to your question is, yes, you can help to reduce the problem by being very precise and careful about the question you're trying to answer. Sometimes you can't be totally precise, of course. Quite often you can't be totally, maybe always you can't be totally precise, but being as precise as you can, that certainly reduces the problem. Okay. And then there's a question by one of our organizers, Emily Gardner, who is interested about the deliberate production of ignorance, agnotology. Does intentionally darkened data contribute to this, or any other type of dark data? Yeah, intentionally darkened data can, as my examples have shown, can enable you to do better or to do things that you couldn't do, like in clinical trials, if you don't hide some of the data, if you don't darken some of the data. But in other cases, intentionally darkened data can lead to all sorts of problems. One of the chapters in the book is on fraud, and fraud is, of course, par excellence the example of people hiding the truth, hiding what's really going on, so darkening the data to detrimental effect. Okay. And now we move on to a group of questions about politics and different countries. And the question from Maria comes that it would be interesting to hear your views on the extent to which darkness is due to policy and political choices on what to show, among other issues you're mentioning. Dark might mean data missing or hidden or shown strategically, leaving aside conspiracy. What are country differences in the awareness around dark data? You're absolutely right. Darkness can be due to policy, political choices. It could be deliberate. It could be sort of accidental. I suppose I'm more interested in the accidental problems, but yes, there are cases, and they're not difficult to find, where data are deliberately concealed, or one can think of things like redefining definitions of unemployment or something like that, so that it appears to show things moving in a particular direction and so on. So data can be strategically hidden, concealed. even subconsciously or deliberately. What are the country differences in awareness around dark data? I don't know is the short answer. I haven't carried out I haven't looked at the differences. I think it's pretty clear that I think, for instance, the UK with its UK Stats Authority, which is independent of government, is pretty good in terms of national data, very good in terms of national data, national statistics, much better than some other countries where you can get political intervention in figures which are produced. I have to say, to detriment, because of the sort of illustrations that I've given earlier. If the numbers are not representing the reality, you're sort of lost. You have no idea where you are. I'm involved with something called the Commonwealth Partnership for Technology Management, which involved national statisticians, central bankers, and so on from Commonwealth countries. And I have spoken to them several times about these issues of dark data, and they've certainly expressed a lot of interest. So, you know, hopefully there are different degrees of awareness, but hopefully understanding of these sorts of problems is spreading.
There's a follow-up question again to the same theme by Terry Fletcher, that now considering that you would know, or that you are conscious that a government has a strong incentive to obscure or statistically present only some variables, what would be the technical methods, or how would you impute the data that considering that you know that something is like systematically there? Would there be any methods for imputing variables then?
Yeah, that's a very good question. I think I don't think it's possible to come up with general methods other than the principle of getting information from some other data source. And of course, the Billion Prices project to measure inflation in South American countries and showing that the official Argentinian inflation rate was very out of line with what the real level of inflation was, is a prime example of that. And of course, there what they did was the official rate got their data, or claimed to get their data in traditional ways, doing surveys of prices in shops and so on, whereas the Billion Prices project scraped prices from the web. There are issues of definition, of course, coming in here. Web prices might be a bit different from shop prices and so on, physical shop prices. But putting those to one side, basically they were getting data from another source. So if there is a general answer to it, that would be it. Get data from another source.
Thank you very much, David. It has been an honor. And to all our 81 participants, please join me with a round of applause by unmuting your mic and clapping.
Thank you very much.